Arc length and curvature. Let's first recall that the arc length of a curve in 2 dimensions is given by the formula you see here. So in 3 dimensions, this is just an extension of that formula to include the third variable z. So to find the arc length of a curve, we have the integral of the square root of dx dt squared plus dy dt squared plus dz dt squared. And this amounted to drawing line segments from one point to another and using the length of that line segment to approximate the length of the curve. So we use that same principle here and we get a similar formula. Now it should be noted that this arc length formula can be summarized as simply the integral from a to b of the magnitude of the derivative of the vector r, where the vector r is simply given by the parametric equations x of t, y of t, and z of t, or if you like, f of t, g of t, and h of t. Next, let's discuss alternative parameterizations of a curve. So if I have a curve r defined by t squared, t cubed, where t ranges from 1 to 2, recognize that the curve defined by r2 equals e to the u, e to the 2u, and e to the 3u, where u is a number between 0 and natural log of 2, gives us the same curve. So these are different parameterizations, but if you were to graph these, you get the same exact curve. Now let's observe why this is the case. If we let the variable t be represented by e to the u, and let's recall that we can do this because if t is a number between 1 and 2, it means that t is positive, and if t is positive, we can express it as e to the u because, of course, e to the u always produces positive values. But if that's the case, then this means that t squared would be e to the u quantity squared, which is e to the 2u, and also t cubed would be e to the u quantity cubed, which is e to the 3u. So you can see that t is the same as e to the u, t squared is the same as e to the 2u, and t cubed is e to the 3u. Now, of course, what are the values of u that produce these same values of t? Well, if t is equal to 1, then this means that e to the u would be equal to 1. And of course, this means that u would have to be the natural log of 1, which we know is 0. And if t equals 2, we get e to the u equals 2, which means that u would be equal to the natural log of 2. So the corresponding numbers for u is u has to be a number between 0 and the natural log of 2. So what we need to recognize here is that when you parameterize a curve, there are different parameterizations that produce the exact same curve. Now let's go back to arc length and think about the arc length function. So if I have some space curve and I want to find the length of that curve starting at some number a and then going to some unknown number, let's call it t, the length of that curve is going to be the integral from a to t, and then we have the magnitude of the derivative of the r vector with respect to u. Now the reason we're using the variable u here is because if we have the variable t in our limit, we have to use a different variable down here. So normally this would be t and this would be dt, but in this case we have to use a different variable. And of course this is equal to the following integral. And now, because of the fundamental theorem of calculus, if you take the derivative of the left-hand side, the derivative of s here is simply going to be ds dt, and that's going to equal the derivative of the right-hand side. But because of the fundamental theorem of calculus, when we take the derivative of the integral here, we get the integrand, which is equal to this here, but we have to evaluate it at the limit t. So long story short, ds dt is the same as the magnitude of the derivative vector. And it's also worth noting that ds dt is a measure of how fast the arc length is changing with respect to t. Now let's take a look at parameterizing a curve with respect to its arc length. Here we want to re-parameterize the helix given by r of t with respect to its arc length measured from the point 1, 0, 0 in the direction of increasing t. So first, let's recall that s of t is equal to the integral from a to t of the magnitude of the derivative of the vector r of u du. Now let's recall here that r of u is simply a change of variable here, so we're just going to replace the t's here with u's. So if I do that, I get cosine of u, sine of u, and u. Now r prime of u is simply negative sine of u, cosine of u, and 1. Therefore, the magnitude of r prime of u is the square root of negative sine of u quantity squared plus cosine of u quantity squared plus 1 squared. And this is equal to the square root of 2. So then s of t equals the integral from 0 to t of the square root of 2 du. And this is the square root of 2 times u from 0 to t, which is the square root of 2 times t. So now I know that s is equal to radical 2 times t. So if I want to re-parameterize this function, all I need to do is take this equation and solve it for t. So t equals s divided by the square root of 2. And now we're simply going to make this substitution into our original r of t. And so r becomes cosine of s over radical 2 times I plus sine of s over radical 2 times j plus s over radical 2 times k. And again, if you were to graph this space curve, you would get the same curve that we got in the beginning. Now let's talk about curvature. A parameterization r of t is called smooth on an interval I if r prime is continuous and r prime is not equal to 0. A curve is called smooth if it has a smooth parameterization. What this means in all practical terms is that a curve is called smooth if it has no sharp corners or cusps or anything like that. So it is exactly what it sounds like. So when the curve turns, it turns softly, not abruptly. If C is a smooth curve defined by the vector function r, let's recall that the unit tangent vector, which we call t of t, is given by r prime of t divided by the magnitude of r prime of t. And this is going to indicate the direction of the curve. So what you see here, all these little red vectors, these are unit tangent vectors. So all we're doing there is basically drawing the tangent line, but then the vector associated with that tangent line is 1 unit long and points in the direction of the motion of the curve. So rather than having tangent vectors of all different lengths, finding the unit tangent vectors is a nice way to graphically illustrate how quickly the curve is changing. Next, we talk about the curvature of a space curve. And this is given by kappa equals the magnitude of the vector derivative of the unit vector with respect to the arc length parameterization. Now let's recall that the derivative of the unit tangent with respect to time can be found by the derivative of the unit tangent with respect to the arc length parameterization multiplied by the derivative of the arc length parameterization with respect to time. And this is just the chain rule. Now, if we solve for dt ds here, we end up getting dt ds is equal to dt dt divided by ds dt. But we can rewrite this as t prime of t, and then let's recall that ds dt is the magnitude of r prime of t. And now kappa, which is defined as the magnitude of dt ds, is equal to the magnitude of this thing, which is t prime of t divided by the magnitude of r prime of t. But this is already a scalar. And because this is a scalar, the magnitude of that is going to equal the absolute value of this number. But again, this is already a scalar and it's positive. So all we have to do is apply this magnitude to the numerator. So we get the magnitude of t prime of t divided by the magnitude of r prime of t. So we end up using this formula when we want to find curvature. And the reason is because this formula here is extremely tedious. You would first have to find the arc length parameterization, and then you would have to use this formula. It's much easier to go straight to the curvature, and to get that, all you need to know is the vector r itself. Let's take a look at an example. So here we want to show that the curvature of a circle of radius a is 1 divided by a. So first we need a parameterization for the equation of a circle. And this is in 2 dimensions, right? Because there's no space involved here. We're simply looking at a circle. So if I have a circle of radius a, we should recall that x is going to be a times the cosine of t, and y is going to be a times the sine of t. So our vector function r can be expressed as a cosine t, a sine of t. So now to compute kappa of t, first we need to figure out the unit tangent vector. And to do that, we need the derivative r prime. So r prime of t is going to be negative a sine of t and a cosine of t. And the magnitude of r prime of t will be the square root of a squared sine squared of t plus a squared cosine squared of t. And this is equal to the square root of a squared, which is equal to a. And so our unit tangent vector is going to be the vector r prime divided by a. And dividing by a is the same as multiplying by the scalar 1 over a. And if we distribute that here, we get our unit tangent vector is equal to negative sine of t cosine of t. And so now we need t prime, and that is going to be negative cosine of t and negative sine of t. And then the magnitude of t prime will be the square root of negative cosine of t, quantity squared, plus negative sine of t, quantity squared. And this, of course, is equal to 1. And so the curvature, kappa of t, will be the magnitude of t prime, which is 1, divided by the magnitude of r prime, which we found was a. And so this is 1 divided by a. This alternative formula for curvature is given by what you see here. Kappa of t is the magnitude of the cross product of r prime and r double prime divided by the cube of the magnitude of r prime. So you might be wondering, where does this formula come from? How do we get that formula from the original curvature formula? Let's go through this derivation. So we want to prove that kappa is equal to r prime crossed with r double prime, magnitude of that, divided by the magnitude of r prime to the third power. Now let's think about what we know. We know that t is equal to r prime divided by the magnitude of r prime. But we also know that the magnitude of r prime is equal to ds dt. So if I substitute this back in here, we get r prime divided by ds dt. Or I can write this as r prime is equal to ds dt multiplied by the unit tangent vector. Now if I take the derivative of both sides, the derivative of the left-hand side is the second derivative, and on the right-hand side I'm going to use the product rule. So we're going to have the second derivative here multiplied by the unit tangent plus the derivative, ds dt, multiplied by the derivative of the unit tangent. So now let's figure out what is r prime crossed with r double prime. Well, r prime is ds dt times the vector t, and we're going to cross that with the second derivative of s multiplied by t plus the derivative of s multiplied by t prime. And due to properties of cross products, we can essentially distribute this here. And this becomes ds dt times t cross product with second derivative of s with respect to t times t plus ds dt times t crossed with ds dt times t prime. Now because t cross t is always equal to 0, this term here is going to cancel out, and we're just going to end up with ds dt quantity squared and then t crossed with t prime. Now if we take the magnitude of this, we're going to get the magnitude of ds dt squared, and then times the magnitude of t crossed with t prime. And this is equal to the magnitude of ds dt squared multiplied by magnitude of t prime times the sine of theta. And this is just from properties of cross products. But we know that t is a unit vector, so that we know the magnitude of t here is equal to 1. And we also know that t and t prime are perpendicular to each other. So we know that theta is equal to 90 degrees, therefore the sine of theta is going to equal 1. And so this simplifies to ds dt squared, we can drop these absolute values here, multiplied by the magnitude of t prime. And so what we have in the end here is the magnitude of t prime is equal to the cross product of r prime and r double prime divided by ds dt squared. But this is equal to the magnitude of r prime crossed with r double prime divided by the magnitude of r prime squared, because remember, the magnitude of r prime is ds dt. And so finally we have kappa, which is equal to the magnitude of t prime divided by the magnitude of r prime is going to equal this quantity here divided by the magnitude of r prime one more time. And so this is the magnitude of r prime crossed with r double prime divided by the magnitude of r prime squared, and then divided by the magnitude of r prime again, and this gives us the magnitude of r prime cubed in the bottom. And that proves this new curvature formula, which in all honesty is going to be the formula that you use. So let's go ahead and find the curvature of it's called the twisted cubic, r of t equals t squared, t cubed, at a general point and also at 0, 0, 0. So to do this, first we need r prime. R prime is going to be 1, 2t, 3t squared. We also need r double prime, which is going to be 0, 2, and 6t. Now we're going to take the cross product here. So we'll do the cross product off camera here, and we'll come back and put that in. And now if we take its magnitude, that is going to be the square root of 36t to the fourth plus 36t squared plus 4. Now let's go ahead and compute the magnitude of r prime. So here is r prime. Its magnitude will be the square root of 1 plus 4t squared plus 9t to the fourth. And so the magnitude of r prime to the third power is simply going to be 1 plus 4t squared plus 9t to the fourth. Now, remember, a square root is a 1/2 power, and then if we cube that, we get a 3/2 power. And so, kappa of t is going to be this quantity divided by this quantity. And if you want, in the numerator up here, you could factor a 4 out, and the square root of 4 is 2. And so you could slightly simplify this. To be this quantity here. And now to find the curvature at 0, 0, 0, all I need to do for that is simply let t be equal to 0. And if we let t equal to 0, we get the curvature at 0 is equal to 2 divided by 1 to the 3/2, which is 2. Now let's talk about the curvature of a function in the plane. So we're going back to 2 dimensions here. If I have some curve in 2 space, to find the parameterization of a point on a curve, remember if this is y equals f of x, we could represent the point by x, f of x. Now if I want to find the curvature using the formula that we talked about previously, I can only do this in R3. So what we need to do is make a 3-dimensional point out of this point. And to do that, it's relatively simple. All we need to do is add a third component and just call it 0. So the graph of this would still be in the xy plane. It's just that the height z would always be 0. So I can parameterize this using the following. R of x is equal to x, f of x, 0. R prime of x would simply be 1 f prime of x, 0. And R double prime of x would be 0 f double prime of x and 0. And now to find the curvature, kappa of x, what I need to do is take r prime of x and take the cross product with r double prime of x, and then the magnitude, and then simply divide that by the magnitude of r prime of x, quantity to the third power. So now we just need to perform these calculations. So r prime crossed with r double prime. So we're going to take the cross product of these two vectors here. Again, let's go ahead and do this off camera. And this simply turns out to be 0, 0, f double prime. Therefore, when I take the magnitude of that, we are going to have the magnitude of this vector, which is simply the square root of 0 squared plus 0 squared plus f double prime of x squared. And this is the absolute value of f double prime of x. And now the magnitude of r prime is simply the square root of 1 squared plus f prime of x squared plus 0 squared. So I'm just taking the magnitude of this vector. And that is the square root of 1 plus f prime of x squared. And now if we cube that, this is going to turn into 1 plus f prime of x squared quantity to the 3/2. All right, so that is what this quantity will end up being. And what we get is the curvature as a function of x is going to be the absolute value of the second derivative of x divided by 1 plus f prime of x squared quantity to the 3/2 power. And this is a way of measuring the curvature of, a regular function, y equals f of x. Let's take a look at an example. So let's go ahead and find the curvature of y equals x squared at the points 0, 0, 1, 1, and 2, 4. So first, let's just compute some derivatives here. So f prime of x we know is 2x. F double prime of x is 2. So kappa of x is going to be the absolute value of the second derivative divided by 1 plus the first derivative, which is 2x, quantity squared, and then raised to the 3/2. So this is 2 divided by 1 plus 4x squared to the 3/2 power. So this is the measurement of the curvature at any number x. So at the point 0, 0, this is x equals 0, we have the curvature at 0 is equal to 2. So all we're doing here is plugging in x equals 0. At the point 1, 1, so this is x equals 1, the curvature at 1 is going to be 2 divided by 1 plus 4, which is 5, to the 3/2 power, which is approximately 0.18. And at 2, 4, which of course corresponds to x equals 2, the curvature at 2 is going to be 2 divided by 1 plus 4 times 2 squared, which is 16, to the 3/2. So this is 2 divided by 17 to the 3/2, and this is approximately 0.03. Now, let's go ahead and take a look at the graph of this function and the graph of the curvature function. So you can see here y equals x squared is here. And it would make sense that the most curvature is going to be right here in this region because this is where it really curves, right? Y equals x squared after that point gets straighter and straighter and straighter. So there's less curvature out here, more curvature in here. And you can see that by looking at the graph of the curvature function. So the closer the curvature is to 0 is basically saying that the curve is relatively straight. So you can see out here where the curve is relatively straight, the value of the curvature function is getting closer and closer to 0. Same thing happens over here. But in here where you have some curvature, you can see that the curvature is maximized at 0, which makes sense because this is the point where the parabola turns around. And that maximum curvature there is 2. Now, if this had curved more dramatically, then this value would be higher. But because this is a relatively soft curve here, the value of the curvature function at 0 is only 2. So the higher the value of the curvature function, the more sharp the curve is. Next, we look at the normal and binormal vectors. So let's consider a space curve, and let's take a look at the unit tangent vector. Now remember, the unit tangent vector is going in the direction of the curve there and has a length of 1 unit. The normal vector is perpendicular to this vector here. And then we have the binormal vector, which is defined to be the vector that is perpendicular to both the tangent vector and the normal vector. So to get the normal vector, all we have to do is take the vector t prime, because we know that the derivative of the unit tangent vector is perpendicular to the tangent vector. So to get the unit normal vector, we just take that vector and normalize it by dividing it by its length. And then to get the binormal vector, it should make sense that it is the cross product of the tangent vector and the normal vector, because the binormal vector has to be perpendicular to both. Now it turns out that these two vectors are very useful in describing motion in space. And so let's go ahead and take a look at an example. So in this example, find the unit normal and binormal vectors for the circular helix. All right, so to do this, first of all, we need the tangent vector, t. And to get that, we need to understand where that comes from. This is simply r prime of t divided by the absolute value of r prime of t. Okay, so let's go ahead and calculate what is r prime. R prime is going to be the vector negative sine of t, cosine of t, and 1. And so the absolute value of r prime, remember we've already done this a couple of times now, this ends up being the square root of 2. And so the tangent vector, the unit tangent vector, is equal to the vector negative 1 over radical 2 sine of t, 1 over radical 2 cosine of t, and 1 over radical 2. So I'm just taking this vector and dividing each component by radical 2. So now we need t prime. To get t prime, we simply take the derivative here. So we're going to get negative 1 over radical 2 cosine of t, negative 1 over radical 2 sine of t, and of course the derivative of 1 over radical 2 is 0. And so to get the normal vector now, we just simply need the vector t prime divided by the absolute value or the magnitude of t prime. And so that is going to be the vector that you see here. Divided by the square root of each of those things squared. So now to get the normal vector, we take t prime and divide it by its magnitude. So let's go ahead and calculate the magnitude of t prime. That's going to be the square root of 1/2 cosine squared t plus 1/2 sine squared t. And this is going to be the square root of 1/2, which is 1 over the square root of 2. And so our normal vector is going to be the vector t divided by 1 over radical 2. When you invert and multiply, you're basically just going to be multiplying each of these by a radical 2. And so this becomes negative cosine of t sine of t 0. Negative sine of t. So this is our unit normal vector. Now to get the binormal vector, b, we simply take the unit tangent vector and cross product with the unit normal vector. And so that is going to be the vector that you see here crossed with the vector that you see here. And we'll go ahead and do this cross product off camera. And there it is. So this next example is really just more practice on all the concepts that we've talked about up to this point. So we have a given parameterization of a curve. We want to find the unit tangent vector, the unit normal vector, the binormal vector, and the curvature. So let's go ahead and start computing these things. So first we'll go ahead and compute r prime. R prime is simply going to be the derivatives of what you see here. So we have 1, we have radical 2 over t, and negative 1 over t squared. We'll go ahead and take the magnitude of this vector. So that's going to be the square root of the squares of each of these quantities. And this ends up being the square root of 1 plus 2 over t squared plus 1 over t to the fourth. And you can use a little bit of algebra here to simplify this, so you can get a common denominator, t to the fourth plus 2t squared plus 1 all over t to the fourth. And we can rewrite this as 1 over t squared times the square root of t squared plus 1 quantity squared. And this becomes t squared plus 1 over t squared, which is 1 plus 1 over t squared. So now the unit tangent vector we know is r prime divided by the magnitude of r prime. So that is going to be the vector 1 radical 2 over t, negative 1 over t squared, divided by, now when you divide, it's actually a little bit easier to divide by this quantity than it is to divide by this one. So I'll just put in that quantity, t squared plus 1 over t squared. This is going to be t squared over t squared plus 1 multiplied by 1 radical 2 over t and negative 1 over t squared. And you can distribute this if you want, or I guess it would be more appropriate to at least just distribute the numerator here. So this becomes 1 over t squared plus 1 multiplied by t squared radical 2t and negative 1. And this is our unit tangent vector. Now for the unit normal, we have the following formula. And so we need t prime. To get t prime, one way to do it here is to take the product rule for a scalar and a vector. So we're going to take the derivative of this times this, and then this times the derivative of this. So let's go ahead and do that work here. So using the quotient rule, you can show that the derivative of 1 over t squared plus 1 is negative 2t over t squared plus 1 squared. Multiply that by the original vector here. Plus, and then now we're going to take that thing, 1 over t squared plus 1, and then multiply it by the derivative of our vector, which is 2t radical 2 and 0. Now, rather than try to simplify this, since they just want the normal vector at the point given, I'm just going to go ahead and plug in the value of t. So let's recall we were doing this at the point 1, 0, 1, and the first parameter was t, so we know that t is equal to 1. So I'm going to go ahead and plug in 1 into t prime. So t prime of 1 is going to be negative 2 divided by 2 squared, 1 radical 2 negative 1, plus, and then if I plug in t equals 1 here, I get 1 half 2 radical 2 and 0. And if we add these together, we get the vector 1 half, 0, 1 half. And so that is t prime of 1. And then the magnitude of t prime of 1 is simply going to be the square root of 1 half squared plus 0 squared plus 1 half squared. And this is the square root of 1 half, which is 1 over radical 2. And so now we can go ahead and give the normal vector here, the normal vector at 1 is going to be t prime at 1 divided by the length of t prime at 1. And so that is going to be the vector 1/2, 0, 1/2 divided by 1 over radical 2. And if you invert and multiply here, we should end up with radical 2 over 2, 0, and radical 2 over 2. And they actually asked for the unit tangent vector at 1 as well. I forgot to do that. So the unit tangent vector at 1, all we have to do is plug in t equals 1 here. And when I plug in t equals 1 here, I get 1/2 times 1. So that's going to be 1/2. And then we're going to have radical 2 times 1/2, which is radical 2 over 2. And finally, negative 1 times 1/2 is negative 1/2. And so this is the unit tangent vector at t equals 1. And finally, for the binomial vector b is going to be the tangent vector crossed with the normal vector. And so the binomial vector at 1 is going to be t of 1 crossed with n of 1. And so that is just going to be the cross product of the two vectors that you see over there. So that is going to be the vector 1/2, radical 2 over 2, negative 1/2, cross product with radical 2 over 2, 0, and radical 2 over 2. And this is the vector 1/2, negative radical 2 over 2, and negative 1/2. Okay, and finally, the curvature. The curvature at 1 is defined to be the magnitude of t prime of 1 divided by the magnitude of r prime of 1. Well, the magnitude of t prime of 1 is the vector 1/2, 0, 1/2. We did that just a few minutes ago. And the magnitude of r prime of 1, we have to go back up to here. Let's find r prime. R prime is this vector. So r prime of 1 is going to be 1, radical 2, and negative 1. And if you calculate that magnitude, you're going to get the square root of 1 plus 2 plus 1, which is the square root of 4, which is 2. And so what we should have here, forgot my magnitude there, we should have the magnitude of the vector 1/4, 0, 1/4. And that is the square root of 1/4 squared plus 1/4 squared, which is the square root of 2 over 16, or radical 2 over 4. So, in summary here, this stuff is not terribly difficult, but it is extraordinarily tedious. And it is very important that you pay very close attention to every detail in every step. Otherwise, it's very easy to make mistakes. And the final topic is something called torsion. Think about torsion as being the rate at which a curve is twisting. So if you're on a roller coaster, you would have the rate at which you move up and down or how sharp the curve is. But when you start moving side to side or like a corkscrew, that's a measure of twist. So torsion is basically how much is the curve twisting. Now, the definition of torsion is the Greek letter tau is equal to negative derivative of the binomial vector with respect to the arc length parameterization, and then we take the dot product with the normal vector n. In practice, though, this is a more commonly used formula, and then we also have a theorem that allows us to find the torsion directly from R, and that is given here. So let's go ahead and compute the torsion for a given curve. So here's an example of finding the torsion of the helix that we've been discussing in multiple examples now. To do this, I need to find r prime, r double prime, and r triple prime. So let's go ahead and start finding those. So r prime is, once again, negative sine of t, cosine of t, and 1. R double prime is going to be negative cosine of t, negative sine of t, and 0. And r triple prime is going to be sine of t, negative cosine of t, and 0. Now what we need to do is take the cross product of r prime and r double prime. So r prime crossed with r double prime. We'll go ahead and do this off camera. And there it is. And now we are going to take that vector and dot product it with the r triple prime vector. So let's go ahead and compute that. So we have r prime crossed with r double prime, and then we are going to take the dot product with r triple prime. And when we perform this dot product, we have sine times sine, which is sine squared of t, plus negative cosine times negative cosine is cosine squared of t, and 1 plus 0 is 1, and so this, or 1 times 0 is 0, so this is going to be 1. So the numerator is 1. Now we need to take r prime crossed with r double prime and find the magnitude. Well, again, we already have that vector right here, and so the magnitude of r prime crossed with r double prime is simply the square root of sine squared of t plus cosine squared of t plus 1, which is the square root of 2. And so the torsion is going to be 1 over radical 2. No, sorry, not 1 over radical 2. 1 over 2, right? Because this was the magnitude squared. So I forgot to square that. There we go. So it's going to be 1/2. Always got to be careful with the details. And if you made it all the way to the end, congratulations. That concludes this video lesson.